All right, so we're going to today look at strength of acids and bases, which can be a little bit confusing. So we'll go through this. First off, we're going to look at this concept of dilute versus concentrated. So dilute is a term you might have heard before. Basically, it just means you have some solute, let's say salt, and the water, and it's just a very small amount of salt in comparison to the amount of water. So it's dilute. You wouldn't even, if you tasted this, you might not even notice there's salt in there. Versus concentrated is basically you have a lot of solute dissolved, so maybe a lot of salt grains put in, and that's concentrated. And if you were to water down this solution, then it would probably become diluted, or you would dilute it, and so you might get to this point depending on how that goes. There's no hard and fast rule on when it becomes concentrated or dilute. It's just sort of a relative term that we use. So now this brings us to this concept of weak versus strong. This is actually a very different thing. So acids, they're kind of like salts a lot of times, whereas they get a positive and a negative part to it. Like NaCl has a Na plus and Cl minus is negative. Here, let's say we have a positive part to the acid and a negative part. So a weak acid, when you dissolve it in the water, only some of them break apart. So like this one here and this one here, but a lot of them remain dissociated, unpopped, if you will. And so a weak acid or base, a lot of it remains undissociated, whereas a strong acid or base, you dissolve it, and virtually all of it breaks apart. So every single one you put in, they all dissociate, they all break. So this chart does a pretty good job showing these two things, because again, weak versus strong is different from dilute versus concentrated. So here is a acid HF. Hydrofluoric acid, it is a weak acid, and it is dilute because I haven't put very much in the beaker. And it's weak because when I put them in, notice that a lot of the HFs remained as HF. Only a couple of them actually dissociated into H plus and F minus. On the other hand, if I put a lot more HF into the solution, it could become concentrated, but it's still weak because of the HFs I put in here, most of them still did not, in fact, dissociate. Compare that to, say, HCl, hydrochloric acid, which is a strong acid. Here it's strong and dilute because I didn't really put a lot in there, but everything I did put in all broke. And if I put a lot more, strong and concentrated, it would look something like this. So the pH is all about how much H plus is in solution. So it's tough to judge exactly. A weak concentrated solution could have a similar pH to a strong dilute solution. It all really depends on how many H pluses you end up with at the end of the day in the solution. Certainly a strong concentrated solution is typically going to have a lower pH than any of these other ones. The other thing to be careful of is, typically, strong acids are considered dangerous because, they have a much lower pH, but it's not a hard and fast rule. HF here, which is a weak acid, is actually a very, very dangerous substance. It's one that you would never want to deal with in a laboratory. It's the way it reacts is just much more violent than any of these other ones, even though it's a weak acid. So it's not a perfect sort of system with that. But anyway, so this chart breaks it down pretty well. Just make sure you understand how this all works. So concentration we've talked about before, the way we measure it, typically with molarity, moles per liter. Again, there's no cutoff between when it becomes dilute and concentrated. And when we buy acids from the laboratory, most of the acids we get come in bottles that are over 10 molarity. Because they don't want to ship a lot of water if they don't have to, and then we dilute them down to the safe concentrations we use in class. And that's sort of how that works. Now, the way we measure acid strength, and this is why we did the equilibrium unit right before this, is something called Ka, which is the acid dissociation constant. And basically, what this is all about is if you take an acid reaction, here's HA, that's not a real acid, it's just a general formula. Mix it with water, it gives an H plus to water to make H3O plus and A minus. If we measure the K value for this reaction, then that gives us Ka. And the idea is if K is really big, this reaction pushes to the right very far. It makes a lot of H3O plus, and therefore it is a stronger acid, because a completely strong acid pushes all the way to the right, and so its K value is very, very large. Whereas a weak acid does not go very far to the right, and so its Ka value is generally considered pretty small. So the bigger Ka, the stronger the acid. And strong acids don't even usually get a Ka, they're just considered very strong. We don't even have to consider it. Anyway, as far as strong acids, there are only 7. If you were going on in chemistry, you would want to memorize these. For now, don't worry about that. Notice 3 of them are halogens, ClBrI. Those are the strong acids. So HF is an exception. It's the only one that is a weak acid of these halogen ones. And these other 4 are just ones that you would encounter frequently and would want to know: nitric, sulfuric, chloric, and perchloric. Every other acid is a weak acid and will have a Ka value to indicate how weak or strong it is. So let's look at 2 acids. So here are 2 weak acids: hydrofluoric acid and hydrocyanic acid. All right, I think it's actually just cyanic acid. Anyway, HF is reacting with water to make H3O plus and F minus. That's the reaction when HF mixes with water. Let's say it's 0.3 molar concentration. So it's going to drop by some unknown amount. These are going to increase by that same unknown, and your equilibrium will be 0.3 minus X for HF, and these will each be X. So the formula for K we talked about before: products over reactants. So X times X, X squared divided by 0.3 minus X. Remember, we ignore water, equals the Ka value. This Ka value is something we would look up or would be in, in a textbook, or this was calculated experimentally at one point, but for now we have them. If we solve for X algebraically, assuming X is pretty small, we can usually do that. We get X equals 0.014, which means that at equilibrium, the concentration of H3O plus is 0.014. And so compare that to if HF were a strong acid. If it were a strong acid, it would all break apart, and H3O would be 0.3. But because it's weak, it ends up only breaking down to 0.014, which is about 3%. So again, it's very weak compared to what it could be if it fully broke apart. Now, HCN has a Ka value even smaller than HF. So when we do this exact same thing with the ice chart, minus X plus X, solve for it, we get an H3O plus of only 0.0000136, much smaller. So the weaker the acid, typically you're going to get less H3O plus in solution. So this will not have as low a pH as the HF, which had more H3O plus at equilibrium. Now, bases, it's the same idea. We measure with a K value, equilibrium. We call it the base dissociation constant, Kb. And this is a general formula for a base reaction. A base reacts with water. And what do bases do? They pull H plus away from something else. So it pulls the H plus off water to become BH plus and then OH minus. And again, B is not a real chemical. It's just a general placeholder I'm using. So the formula for Kb, OH minus times BH plus over B. Same deal as acids. The bigger K is, the stronger the base, and larger Ks, that's what a strong base would look like. Strong bases, pretty much all you need to know with strong bases is if you see a metal with an OH, then it's a strong base. All the alkali metals with OH are very strong. The alkaline earth metals are also strong, although they are not as soluble in water. You're not going to get a 2 molar solution of MgOH2. It just won't dissolve. You can get a 2 molar solution of NaOH, and that will fully dissolve and break apart, but these are just very small solubility, so you won't see them much. They fully break apart, and these fully break apart too, like they'll lose both OHs in solution. But let's look at some weak bases. Weak bases, you treat them pretty much exactly as you do weak acids. You set up the formula with an ice chart, reacts with water to make, in this case, it's pulling the H plus away from water to make NH4 plus and OH minus. We set up our lines, we solve for X, and in this case, X is how much OH minus there is, 0.0023. So ammonia had a Kb of this, and it's at a concentration of 0.3. At equilibrium, its OH will be 0.0023. Again, if this were NaOH, 0.3, you would have 0.3 OH minus at equilibrium. That's not the case here. The next one, Kb, is smaller, and so we get a smaller OH minus. So this first one had more OH, so its pH is going to be higher, because again, it had a stronger Kb, and this one had less OH, so its pH will be lower. So anyway, the math stuff, there's more videos. I go into detail more and break down the calculations for you. So if you miss the math concept, that's okay. But the big thing is just make sure you understand, the difference between weak and strong, dilute and concentrated, and you have some familiarity with these ice charts before you move on. So that's it. Until next time, I am Derek Genova. Have a delightful day.